All right, let's jump right into this explainer. I want to put you right in the hot seat, right off the bat. Imagine for a second that you're an elite engineer, and you've just been tasked with using artificial intelligence to catch bank fraud in real time. We're talking millions of transactions swiping through your system every single hour. Your one and only job is to separate the everyday, normal purchases from the criminal ones, and you have to do it without slowing down the customer experience even a little bit.
Right out of the gate, you're facing what we like to call a violent constraint. You have a strict service level agreement, an SLA, that requires a definitive decision in exactly 100 milliseconds. Think about that. When a customer taps their card at the grocery store, you literally have a fraction of a heartbeat to decide, do we let this payment go through or do we freeze the account?
But, well, here's the massive problem staring you right in the face. Calling a standard large language model to make that kind of nuanced decision takes somewhere between 2 to 5 seconds. In the world of real-time finance, taking 5 seconds means you've instantly failed your deadline. The transaction time's out, the customer is standing there furious, and your whole system practically collapses.
Which brings us to Section 1, perfect code versus messy reality. You see, this specific latency trap, it's exactly why pristine, out-of-the-box AI so often falls flat on its face in the real world. I mean, it works beautifully in a tightly controlled demo, but it completely breaks down when it hits actual enterprise constraints. This friction point exposes a concept we call the delta. The delta is that chaotic, unpredictable gap between a core software product and a client's messy, real-world mission. And this is the exact operating theater of technical special ops. A hybrid role known as forward-deployed engineers, or FDEs. These folks don't just write code, they deploy forward right into the chaos.
Think about the difference here. Traditional software engineers are typically building for millions of anonymous users in a clean, uniform cloud environment, right? They're spending like 90% of their time just building features. But FDEs, it's a whole different ballgame. Their work is 50% high-level strategy and 50% what we call glue code. The incredibly critical custom integrations you absolutely need to survive in hostile legacy environments.
Because out on the FDE battlefield, these engineers aren't just squashing minor software bugs. No, they are deep in the trenches, navigating 20-year-old SQL databases. They're working on air-gapped servers that don't even have an internet connection out at the tactical edge. They're dealing with corrupt data schemas, and of course those extreme latency constraints we talked about. They are the ones tasked with making advanced AI actually survive in the wild.
Let's move on to Section 2, the real-time latency trap. So tying this back into our bank fraud scenario, let's look at exactly why a naive AI architecture just crashes and burns when it hits that 100-millisecond wall. The most common mistake teams make is relying on what we call the naive architecture. Basically, if you try to route every single transaction directly through a massive language model, the system is going to fail. And what's really crucial to understand here is that it doesn't fail because the AI is dumb. Not at all. It fails because it is fundamentally the wrong tool for raw speed. It all comes down to understanding this one fundamental split. Deterministic machine learning models are incredibly fast. We're talking usually under 10 milliseconds. They're super cheap to run at scale, and they're absolutely perfect for binary yes or no classification. On the flip side, probabilistic LLMs are slow, taking those 2 to 5 seconds, and they are really expensive per call. But their core strength? That's deep, nuanced reasoning and explanation. If you treat these two distinct tools as interchangeable, you are going to fail. Period.
And this is where we get to the solution. Section 3, the two-tier AI architecture.
So how do you actually hit that 100-millisecond SLA without totally sacrificing the intelligence of generative AI? Well, elite forward-deployed engineers use this incredibly elegant setup. Let's break down the mechanics of how it actually flows. In step 1, a blazing fast deterministic model, something like XGBoost, makes the hard, real-time binary call to either allow the transaction or flag it, all in under 10 milliseconds. Boom, latency constraint met. Then in step 2, the generative LLM is triggered asynchronously. 5 seconds later, completely removed from the pressure of the customer tapping their card, the LLM generates this comprehensive, deep dive explanation of exactly why the transaction was flagged so a human fraud analyst can review it.
So why does this architecture succeed so consistently out in the real world? It's simple, really. It all comes down to a razor-sharp separation of duties. Tier 1 strictly owns latency. Tier 2 strictly owns reasoning. At no point does either system ever step into the other's job. The heavy, slow LLM is just completely removed from that critical, time-sensitive path.
Let's zoom out a bit for Section 4, where the model belongs. This actually brings us to a pretty universal truth in enterprise AI engineering. Are you ready for it? Not every single decision actually belongs inside a generative model. Take workflow agents, for example. Instead of relying on a slow, expensive LLM to dynamically plan out every single step of a given process, FDEs use deterministic workflow agents to hard-code the sequences we already know. We only bring the LLM into the loop at specific, targeted decision points where genuine ambiguity actually exists. It's about deploying intelligence surgically, not just throwing it at everything indiscriminately.
And the coolest part? This isn't just a banking thing. This exact two-tier architecture is absolutely mandatory across multiple high-stakes industries. Whether you're dealing with medical triage in a busy hospital, high-frequency algorithmic trading, massive-scale content moderation, or defense operations out at the tactical edge, anywhere you have a hard, real-time constraint combined with a need for deep reasoning, this architecture right here is the definitive blueprint. Because at the end of the day, system design really boils down to this one idea. An LLM in the wrong layer isn't a smarter system. It's just a slower one. Indiscriminately throwing generative AI at a problem absolutely does not guarantee you're building an intelligent system. Honestly, more often than not, it just guarantees failure at scale. So to wrap up this explainer, I want to leave you with a final thought to really challenge yourself. The next time you look at your own enterprise AI deployments, or even just the software you use every single day, ask yourself, are you forcing a reasoning engine to do a decision engine's job? Is your LLM sitting right smack in the middle of your critical path, causing massive bottlenecks? Or is it finally placed exactly where it belongs? Think about that as you go architect your next big solution.